All right, here we go. So this is all going to be leading up to something that we're going to do at the end of the unit, which is called optimization problems, which optimization just means finding the optimal or best way of doing something, and that usually involves finding the maximum or minimum value of a function. So like, for example, if you're a business, you might have a profit function that involves whatever you're producing as your variable, and you have, different terms that involve things like costs, and you're trying to optimize profit and figure out, okay, how much of this product should I produce to optimize profit? Then you want to find basically the maximum value of your product function. So they really can just be reduced to finding the maximum or minimum value of a function. So first, let's talk about what we mean by maximum and minimum. Pretty intuitive. You guys have probably worked with this before. So for this function on this interval, its maximum is 5. And its minimum is 2. And so when we say maximum or minimum value, we're talking about y values, not x values. So if I ask, what is the maximum value? I mean the y value. If I ask, where does the maximum occur? I mean the x value. If you want to be safe, you can always just give me the full coordinate, okay? But that language is very important, right? You need to know the difference between location, which is an x value, and value, which is a y value. All right, then we have these definitions of absolute maximums and absolute minimums. So an absolute maximum value of f on D, so f of c, I say, is an absolute maximum if it's greater than all other values of f of x for all x in D. So because we're often talking about continuous functions that don't have boundaries, there is an example of an absolute max. And then an absolute minimum is the opposite. So f of c is an absolute minimum if it's less than or equal to f of x for all x in D. And so that would just be like, whoops, the opposite of that. So if I had like a function like this, a synonym for absolute, sometimes you'll see them use the phrase global. It means the same thing as absolute. So global max or global min still means absolute max and absolute min. Same thing. All right, so why that conditional statement before it? Why not just call it a max or a min? And the reason is because we also have functions like, say, a cubic. Where there is no absolute max or absolute minimum because the graph keeps going upwards indefinitely and also goes downwards indefinitely. So there's no absolute maximum or absolute minimum, but we still have this interesting behavior here and here, right? And so that's not an absolute max, and this is not an absolute min, but it is a type of maximum, and it is a type of minimum, and we call them local. That's a local maximum, and this is a local minimum. And what we mean is local to the points nearby. So if I just look at the points kind of surrounding that point, so just like here, yeah, that's a type of maximum, right? If I just look at the points surrounding this point, that's a type of minimum. It's just not absolute, it's local. All right, so a couple important points. A little bit of a nuance. You can have a point that's both an absolute extreme value and a local extreme value. So like f of d is both an absolute and a local maximum. It's absolute because it is the highest point that the graph attains, but it's also local because I can focus on what we call a neighborhood of points surrounding it that it's larger than. F of a is an endpoint, so we're not looking at a function that continues on indefinitely in both directions. It has endpoints, right? F of a is the lowest. It is only, however, the absolute minimum. It is not a local min because I can't contain a neighborhood of points around it because there's no points to the left of it. Whereas like the point up here, I could contain it within a neighborhood of points on both sides. So it could have a local, it could be the local maximum as well. So the definition, to be able to have a local max or a local min, it has to be contained within a neighborhood of points on both sides. If it's an endpoint, it can be the absolute minimum or absolute maximum, but it will not be a local min or local max. Does that make sense? All right, in the chat, how would you classify the point f of b here? How would you classify that point? Is it an absolute max, an absolute min, a local max, a local min? Oh, Vincent, don't yell it at me. I agree with you guys. It's a local max. It's not absolute because it's not the highest point, but it is local because we can find a neighborhood of points that surround it that it's larger than. All right, how would you classify f of e? Local min, yes. It's not the lowest point, so it's not absolute, but it is local. How would you classify this endpoint? All right, I'm going to give it to you guys. It was a trick question. It's not a local max because yeah, it's just an endpoint. It's not a local max because it can't be contained within a neighborhood of points on both sides. So it's nothing. I agree. It's just an endpoint. It was a trick question. All right, I think we've got the vocab down. I also just realized that you guys had the answers right here. So now I'm not as impressed. I'm just kidding. All right. So there's our definition about local max and local min. So you just need, for local max, you just need f of c to be bigger than f of x when x is near c. And what we mean by near c is that it's true on some interval, on some open interval. It doesn't matter how small, right? So I could have a graph that goes like that. And guess what? That is still a local max. Because even though it's tiny, I can still contain it within an open interval. So I would go here to here, where that vertex is bigger than all the surrounding points in that open interval, right? So any open interval that you can contain, where your highest point or your lowest point is bigger or smaller, respectively, for local max and local min, then that is true. Okay. So that's just a visualization. And the last one, just note that this would be an local and absolute minimum because it's contained within an interval, but it's also the lowest of all points on the graph. All right, where does cosine x take on its local and absolute maximum and minimum? So cosine is a wave function. And it continues indefinitely, and actually at every vertex, it has both a local and absolute extreme value. All right, so where do those happen? What we'll do is establish a pattern. So it has its local / absolute maximums. And actually, let's say this. Where? What are they referring to? X values or Y values?
X.
Good. So they're asking us for a location, so they actually want the X values. They're not asking us for the actual maximum and minimum values. They're asking us for where they occur, so just the X values. So those are going to occur at X equals, and what we'll give ourselves for local max is just a starting point. So the first time it's going to occur is at X equals 0. And then the period of cosine is 2 pi. So you can see it's going to appear every 2 pi after that. We're going to hit a new local max. So the next one over here would be at 4 pi and so on. So I'll do 0 plus 2 pi k, where k has to be an integer. So remember that this means, integer. So k could be 1, and then I would get x equals 2 pi, and that gives me this local maximum. K could be 2, and that would give me x equals 2 pi times 2, or, k could be 1, and I would get this one. K could be 2, I would get 2 pi times 2, and that would be 4 pi. That would give me that maximum. K could be negative 1, and that would give me x equals negative 2 pi, which is going to be over there, right? I think we all agree that's just a perfect continuation of that graph. Basically, it looks like the computer drew it, not a human hand. All right. Local minimum / absolute minimum, same deal. We'll create a pattern, but we're going to have a different starting point. So let's just start it from here. You can see the minimum occurs at pi plus, again, if I add 2 pi to that, I would get my next minimum. So 2 pi k, again, where k has to be an integer. All right, example 1 down. The extreme value theorem. This one has a name, so it's important. And it says if f is a continuous on a closed interval. So we're talking about a function that's continuous on a closed interval, a to b, then it has to attain an absolute maximum and an absolute minimum at some point on that interval. So any function that's continuous on a closed interval. The closed interval part just means it has to have endpoints. Any function that's continuous on a closed interval will attain a maximum and a minimum. Specifically, an absolute maximum and an absolute minimum. The way I drew it, those would be the endpoints. All right, so just a couple things to note for yourself. Here are a couple examples, but your function can attain an absolute maximum or an absolute minimum more than once. That's fine. We saw that with cosine. It hits its absolute maximum infinitely many times and its absolute minimum infinitely many times. If either hypothesis, so continuity or closed interval, is omitted, then the extreme value does not hold. Your function doesn't have to hit an extreme value. For example, if it's discontinuous, it could look like this. This function has no maximum value. The reason being, it's bounded by 3, right? It's bounded on top by 3, but it never attains the value 3. That's an open point. So you can't define a maximum value. I could go, what's the maximum value? And Vincent could go, I'm a pro at maximum and minimums. The maximum value is 2.99. And I go, oh yeah? But 2.999 is also a part of that graph. And so is 2.999, and so on and so forth. So it never attains a maximum. It's bounded by 3, but it never reaches 3, so there's no maximum defined there. The other thing, if it's not a closed interval, then you could have like a vertical asymptote at one of the endpoints, and then this just gets infinitely large, and there's no endpoint, right? So this is an example of a function that has no maximum or minimum, because again, that's an open point. So it's bounded below by 1, but it never actually reaches 1 on the bottom. So you need both those conditions for the extreme value theorem to hold. All right, so it says that there's an absolute maximum and minimum if those conditions hold. So how do we find them? Well, we've already kind of noticed this. What seems to be happening at these local maxima and minima? What calculus characteristic do they have at those points? Horizontal tangent, which means what's the value of their derivative at those points? Awesome. So very important characteristic. We can see that f prime of c is 0. and that f prime of d is also 0. And the only other place that an absolute maximum or minimum could occur at a closed interval is going to be at one of the endpoints. Right? All right. So that's Fermat's theorem. Fermat's theorem says that if a function has a local maximum or minimum at C and f prime exists, the derivative exists, then the derivative will be 0. All right. So we can use that to our advantage. Note that that's local maximum or minimum. Local could also be absolute, but we'll have to check that. So an example I can show you is that the inverse of this statement is not true. So the inverse of this statement being, just because f prime of c is 0 doesn't guarantee that there is a local maximum or minimum at c. Right? This is what we call a conditional statement, and the inverse of a conditional statement isn't always true. So it is true if I say, if I live in Phoenix, then I live in Arizona, right? But if I invert that and say, if I live in Arizona, then I live in Phoenix, no, not necessarily. I could live in beautiful Yuma and go to the Yuma High School where their mascot is literally the criminal. They're the Yuma Criminals. In 2021, that's their mascot. Insane. All right. So the inverse of this statement, not necessarily true. And we can show that with f of x equals x cubed. So let's do this. So take the derivative, f prime of x would be 3x squared. By Fermat's theorem, I'll take that, I'll set it equal to 0, and I'll try and solve for x to see where the derivative is 0, right? So solving for x, I'm going to divide by 3. X squared equals 0. I'm going to take the square root. X equals 0. So I found that there's going to be a horizontal tangent at x equals 0. That's definitely true. We can see that visually here. But that is not a local maximum or local minimum in this case. So all that Fermat's theorem says is that if there is a local maximum or minimum and the derivative exists, the derivative at the local max or min will be 0. We are going to find out that that's still a point of interest to us because there's something going on there, but we'll define that later in the unit. And you can see it's kind of the change in the shape of the graph. It goes from being curved downwards to being curved upwards at that point. We'll define that later, as I said. All right. Another thing that Fermat's theorem can't do for us, you could have a minimum like in the absolute value function, but the derivative won't exist there. So again, Fermat's theorem just says if the derivative does exist at a local max or local min, the derivative will be 0. But you could still have one, a local minimum or a local maximum, and the derivative does not exist at that point. All right, so those two examples are just showing us that we have to be really careful when we use Fermat's theorem. Even when f prime at a point does equal 0, there doesn't have to be a maximum or minimum. And there could be an extreme value when the derivative doesn't exist, like example 3. All right, let's define a couple things. We call a critical number or a critical value a number c such that f prime of c equals 0 or does not exist, because that seems to be where all the interesting stuff happens. When the derivative either equals 0 or doesn't exist. And then our definition below that is that if our function has a local max or min at a point, then that point will be a critical number of the function. All right, so this all culminates in how to find a maximum or minimum value on a closed interval, and we use this thing called the closed interval method. So if it's on a closed interval, we know that it has endpoints. And basically your function, you can find where it attains its extreme values using this method. So find the critical numbers of f in the open interval a and b. So this just involves taking your derivative and setting it equal to 0 and solving. Now your maximum and minimum values are either going to be happening at your critical values or at your endpoints. So once you know your critical values, plug those back into your function to get the y values of the function at those points. And then plug in your endpoints to your function to get the y values there. Whichever one gives you your largest y value, that's your absolute maximum. Whichever one gives you your smallest y value, that's your absolute minimum, and you're done. All right. Yeah, so all we have left is one example. So I'll wait for you to copy this down. Again, give me a hand raise when you're good, and we'll do that example. All right. So let's use the closed interval method to find the absolute maximum and minimum values of this function on the interval from -1/2 to 4. So basically we know that the absolute maximum or minimum could occur at the endpoints so we'll say could occur at f of -1/2 or f of 4, or they could occur at critical values. So the first thing I want to do is find the critical values. All right, and critical values just involve taking the derivative, setting it equal to 0, and solving. So f prime of x equals, that's going to be 3x squared minus 6x. All right, I'm going to set that equal to 0. We're going to solve for all values of x. So I can factor out 3x, and I'm left with x minus 2. And I can just set those separately equal to 0, and I get x equals 0 and x equals 2, right? All right, so those are two other points where my critical values could occur. F of 0 or f of 2, sorry, not that my critical values could occur. Those are critical values, that my absolute maximum or minimum could occur. So now we've listed out all the possible places where we could attain an absolute maximum or an absolute minimum. So all we're going to do is plug those values into our original function. Whichever one gives me back the largest y value, that's my absolute maximum. And whichever one gives me back the least y value, that's my absolute minimum. So let's do this in the calculator just to keep from making an error. Whoops, I need to share that with you. So probably the fastest way to do this, the way I like to do it, hold on, I need to put this back in function mode. All right, I'll just put it in y1. So we're putting our original function in there, x cubed plus, nope, minus 3x squared plus 1. And then I can just go to my table and I can input those values that I wanted. So I wanted f of negative 1/2 All right, that gives me 0.125. I wanted f of 4. That gives me 17. I wanted f of 0. That gives me 1. And I wanted f of 2. That gives me negative 3. So there we go. And now we can name what our absolute max and absolute min are. So I have 17 as my absolute max. That's the largest y value. Negative 3 at my absolute min. So my absolute max occurred at an endpoint, but my absolute minimum occurred at a critical value. So let's just look at that function. So all right, so we're only focused on this function between negative 1/2 and 4. So I'll put those endpoints on the graph. So negative 1/2. So there's my left endpoint, and 4. Oh, come on. All right, there's my right endpoint. So ignore everything outside those points. One of these days I'll look up how to tell Desmos a domain for a function. I just keep forgetting. Nope, that's not the command. No, okay. Anyway. All right, so we saw that on that interval, 17 is our absolute maximum, but the point 2, negative 3, this one is our absolute minimum. And again, that's because I'm only looking at the function between the purple and the black points. Ignore everything outside those points. All right.